Remember that a polynomial, univariate polynomial, is all we need. P, I'll use the notation f bracket x, is a function from the field to the field such that it can be expressed P of this field element, x, whatever it might be, is some coefficient of 1 plus the sum of powers of x multiplied by coefficients. And it's a finite sum, so there's some m such that am is the largest non-zero coefficient. And in that case, we say that this polynomial has degree m. Degree is the largest, the exponent corresponding to the largest non-zero coefficient. We say that some field element lambda is a root of a polynomial p if, definition, p of lambda is equal to 0. Remember that we're working over different fields here. We're thinking about the complex field, complex numbers. I could set p of x equal to 1 plus x squared, and its roots would be I and minus I, where I is the square root of negative 1. Let's mention a couple of things about roots. So let P be a polynomial of degree at least 1. Then lambda is a root if and only if there exists a q, another polynomial in f of x of degree 1 less, such that I can factor p of x as x minus lambda times q of x. And for the proof, you should just look in the book. But for example, our polynomial 1 plus x squared factors as x minus I, and for the root I, x plus I for the root minus I. And one result of that is that a non-zero polynomial of degree m has at most m roots. That's because we can sort of peel off the roots, factor them off one by one. And so when you hear about something like peeling something off, that means you're going to see an induction. So to say that the degree of the polynomial is 0 is that it's constant. And since it's non-zero, it has no roots. That means it's just a constant, which is not 0. If m equals 1, then p of x is some constant plus some coefficient times x to the 1. And this coefficient is not 0. Otherwise, its degree would be 0 or higher. This is the highest non-zero coefficient. And so minus a0 over a1 is a root. And it's legal to divide by a1 because we assumed it's non-zero by saying the degree was 1. And for m greater than 1, we do an induction. The hypothesis is that every polynomial with degree smaller, degree 1 smaller, degree m minus 1, has at most m minus 1 roots. If our p has no roots, then we're done. If our p has a root lambda in f, then we can, by the previous proposition, factor out that lambda, and what's left over has degree m minus 1. And so by hypothesis, the induction hypothesis, this Q has at most m minus 1 roots. So the last polynomial result, I think this is maybe actually the last one I need for you, but you might be able to start with eigenvalues next time. The last one I want to talk about is division. With a remainder. So suppose P and Q are polynomials, and P is not 0. Then there exists other polynomials S and R such that Q is equal to SP plus R. So we've divided by P and kept track of the remainder. And in this case, the degree of R is less than the degree of P. So the proof of this is polynomial division algorithm, which hopefully you've seen in the past.